Okay, great. So far, we've seen assumptions 1 and 2. Here's the third one. It comprises 3 parts: normality, zero mean, and homoscedasticity of the error term. The first one is easy. We assume the error term is normally distributed. Normal distribution is not required for creating the regression, but for making inferences. Remember all regression tables were full of t-statistics and f-statistics? Well, these things work because we assume normality of the error term. What should we do if the error term is not normally distributed? Yes, that's right, the central limit theorem. For large samples, the central limit theorem applies for the error terms too. Therefore, we can consider normality as a given for us. What about a zero mean of error terms? Well, if the mean is not expected to be 0, then the line is not the best fitting one. However, having an intercept solves that problem, so in real life it is unusual to violate this part of the assumption. And homoscedasticity? What's that about? It means to have equal variance. So the error term should have equal variance one with the other. What if there was a pattern in the variance? Well, an example of a data set where errors have a different variance looks like this, starting close to the regression line and going further away. This would imply that for smaller values of the independent and dependent variables, we would have a better prediction than for bigger values. And I assure you, we really don't like this uncertainty. Let's see a real-life example. Most examples related to income are heteroscedastic with varying variance. If a person is poor, he or she spends a constant amount of money on food, entertainment, clothes, etc. The wealthier an individual is, the higher the variability of his expenditure. For example, a poor person may be forced to eat eggs or potatoes every day. Both meals cost a similar amount of money. A wealthy person, however, may go to a fancy gourmet restaurant where truffles are served with expensive champagne one day and stay home and boil eggs the next day. The variability of his spending habits is tremendous. Therefore, we expect heteroscedasticity. Well then, is there a way to circumvent heteroscedasticity? First, check for omitted variable bias. That's always an idea. After that, you can look for outliers and try to remove them. Finally, we shouldn't forget about a statistician's best friend, the log transformation. Naturally, log stands for a logarithm. For each observation in the dependent variable, calculate its natural log and then create a regression between the log of y and the independent x's. Conversely, you can take the independent x that is causing you trouble and do the same. Let's see an example. This is a scatter plot that represents a high level of heteroscedasticity. On the left-hand side of the chart, the variance of the error is small, while on the right, it is high. Here's the model. As x increases by 1 unit, y grows by b1 units. Let's transform the x variable to a new variable called log of x and plot the data. This is the new result. Changing the scale of x would reduce the width of the graph. You can see how the points came closer to each other from left to right. The new model is called a semi-log model. What if we transform the y-scale instead? Analogically to what happened previously, we would expect the height of the graph to be reduced. That's the result. This looks like good linear regression material, doesn't it? The heteroscedasticity we observed earlier is almost gone. This new model is also called semi-log model. Its meaning is, as x increases by 1 unit, y changes by b1%. This is a very common transformation. Sometimes we want or need to change both scales to log. The result is a log-log model. We shrink the graph in height and in width. This is the result. The improvement is noticeable, but not game-changing. However, we may be sure the assumption is not violated. The interpretation is, for each percentage point change in x, y changes by b1 percentage points. If you've done economics, you would recognize such a relationship is known as elasticity. All right, we are done here. 3 assumptions down, 2 to go. Great work!